So far, at least what we saw numerically is the following thing. At least for the binary erasure channels, and in fact only for the binary channel with erasure poly 0.3, we have made the experiment, right? Perhaps if I made the experiment not from 0.3 but maybe 0.2, perhaps you would have not gotten this picture. You don't know this, okay? And secondly, I mean, there are many other channels than the binary erasure channel, okay? For this same phenomenon of becoming good or bad, would this happen? We have no clue, okay? But at least we know that for one data point, it seems to work nicely. Trust me if I say that I made this experiment for the other kinds of binary erasure channels, you get the same picture too. Actually, we could do it, but it's going to be pointless, I think. So let me first try to give you a quick proof that at least for the case of the erasure channels, everything works out okay. We will subsequently do the same argument for general binary channels, binary input channels also. But today, I think just because you have seen for the case of the BEC, the binary erasure channel, how exactly things work, I think it will be a good place to start because you have a picture in mind already. You have seen numerics. By the way, any questions so far? Because I'll be very happy to discuss further. Yes, sir.
Is it a rule that we start decoding from U1?
We have to because of the following thing. The way that we constructed these synthetic channels is such that you have to decode U1 before you decode U2, okay? Because you cannot have the synthetic channel W plus, whose input is U2. We cannot even realize that channel at the receiver before decoding U1. So the receiver has to first decode U1 to be able to obtain what is the output of the channel W plus, because you don't realize the output of W plus without realizing the input of the W minus. Okay? Now, if you have more than these things, you have to be very careful as to which order you do this stuff. Okay, maybe I should not have erased the previous picture, but let me just put it back in. True. Yes, of course. That's what indeed. So, very good point. Let me say this. So, in the example, we saw that we created 70% approximately these perfect channels and 30% terrible channels. So I said I should not use the terrible channels, but of course I'm supposed to send something on them. So we send fixed known symbols known to the transmitter and also to the receiver. So the receiver can decode the input of these bad channels because he knows them a priori. Okay? So we still send bits across them, but they're not data bits. They're what is called in the terminology of polar codes frozen bits. So we send I don't know why. Who came up with this frozen? I have no idea.
Makes sense.
So, yeah. On the others, you send tropical bits. So we send tropical bits on the others, okay, and then we send frozen bits on the bad channels. So these frozen bits, suppose they're all 0, okay? So that so the receiver and the transmitter, they know what they're supposed to send, and then the receiver, when he needs to decode those bad channels, he doesn't need to do any work. He just simply copies what he already knows from before. Okay? And decoding order needs to be the following type, because so there is these channels that you realized. Suppose after 2 transformer, you do this. You decode this one first, okay, to get the input of that one, because the input of this appears at the output of that. And then you decode this one, okay, and then these 2 things that you decode, this particular thing, and if you know this one, then you do that, okay. So we'll go through how the decoding works in a bit more detail shortly, okay. But you're absolutely right that the decoding order needs to be very specific. If you try to start from decoding this, you cannot, because the output of that is the Y1, Y2, Y3, Y4, together with the U1, U2, and U3. So the decoder does not have the output of this channel yet, so you cannot start from this one. You have to start with this channel, whose output is Y1, Y2, Y3, Y4. Receiver has it. So you can do the decoding methods, maybe copy-paste, okay, maybe actual decoding to obtain the U1. Once you obtain the U1, then at the receiver side, you have the output of this particular channel here. You decode that to obtain U2. Once you have this U1 and U2, you have the output of this channel. You can decode the U3. Once you have the U3, you have the U1, U2, U3 in your hands, Y1, Y2, Y3, Y4 in your hands, and you can decode. Okay. And some of these U's are going to come from actual decoding effort. Some of these are going to come from, because they're frozen, you know already what they are. Is this more confusing, maybe, or is it more clear? Am I polarizing the audience in the meantime? Okay. Please ask, because we have tons of time. I mean, I think 9 hours is a way too long amount of time to allocate to polar codes. I can do repetition coding and teach you the same class 3 times. But now let's see what happens for the erasure case. I'm going to try to write here a table in the following way. Let me first of all denote by, suppose P is the erasure probability of the channel W, and I'm going to denote by P plus the erasure probability channel W plus, which is P squared, okay, and then P minus erasure probability of W minus, which is P times 2 minus P. This guy is less than or equal to P. This guy is more than or equal to P, but their average is P, okay? So the P plus P minus equals 2P. So we have a conservation of erasure probabilities we have. So our transformation rules, they don't create more or fewer erasures in this particular thing. Okay. In the meantime, let's also take a look at the, this is smaller, this is bigger. So if you take a look at the P minus P plus, okay, how much discrepancy, how much inequality I have created between the two channels. You see, I started with 2 equal copies. They were both P, 2 of these W's. I just transform, I create inequality. I create injustice. Okay, whatever you want to talk about this. This is equal to 2 times P times 1 minus P. I think it is correct, right? So the, yes, okay. All right. So this is a, maybe I should even take a look at the half of this, so I get rid of this P. Okay. I'm not sure if I really want to divide by half or not, but let us do it for a second. So this guy, if I plotted this thing across P, okay, so this value of this inequality I create, it is something like this. Right. So what you see is the following thing. The amount of inequality you create, okay, is positive, okay, unless you're already extremal, okay, unless you already start with a perfect channel, or unless you start with a completely erase everything channel. The 2 channels that you create are going to be strictly different than each other. Okay, so this difference between the P minus and P plus is strictly positive unless P is extremal. Indeed, you have the following thing, that if P is away from the extremes, if you start with a P which is strictly away from the 2 extremes, it is between delta and 1 minus delta, okay, then the difference in the things, the P minus and P plus, this is at least as big as delta times 1 minus delta, because the minimum, if I told you the P is between here and here, if it is between the delta and 1 minus delta, the smallest possible value of the discrepancy happens at the 2 ends, which is, in either case, it is delta times 1 minus delta. So we have that. Okay, that's, this implies this. This is going to be important for our purposes in a second. Okay, all right, good. Now what I'll do now is the following thing. I'll create a table. The table is the following. In the beginning, I start with P. Okay. And then I have here P plus and P minus. This is the next column of the table. I apply the transform once. I get these 2 numbers here. The next column of this table is P plus plus, P plus minus, P minus plus, P minus minus, which I derive from the second column maybe it's called the zeroth column, let's say, because there's 0 signs on the top of the P. The first column, the second column, okay, and so forth. Here I have, there are 8 of these things, P minus minus, etc. Okay? In general, I have here a whole bunch of sign sequences. Okay? So this is, at some moment here, I have P, whole bunch of minus signs, P, whole bunch of plus signs, and the table continues like this. The ith row, sorry, the ith column of this table contains 2 to the I numbers. Okay? All right. So the I flip the plus and the minus. Thank you. All right. I'll compute the following things. I'm going to compute statistics on these columns. Okay. Very simple statistics. I'm going to compute the mean, the average value, just numerical averaging of these columns here. Okay. That's the, let me call the average, what do we call them? Mu. Okay. So the mu 0 is the average of the first column. Well, there's a single number whose average is P. Okay. What is the average of the first column? It's P again. So mu 1 is equal to P. What is that of the second column? Again P, because the average of these two is P plus. The average of these two is P minus. Okay. Average of these two things is P. So okay. So average is preserved. Okay. So mu 2 is also P, so forth. Okay. So these mu's are the simply straight, ordinary, run-of-the-mill, vanilla average of these columns. They are like that. Okay. Okay. Good. So so forth. So the mu's are constant. Very nice. So the average is not changing. All right. Not interesting. The second I'm going to compute is the second moment of these numbers. What I'll do is I'll square this number and add them and take their average. Okay? So I call them to be, let's say, nu's. Okay? So nu 0 is P squared. This is the average of the squares of these numbers here. So maybe I should write this thing down as to what I'm talking about. So mu I is the average of these 2 to the I numbers in the ith column, okay, over all sign sequences of length I, all the possible plus minus sequences repeated I times. There are 2 to the I things in the summation, P to the S. Okay, so this S is a sign sequence, right? It's not a number. I'm not squaring the P. I'm just simply saying here. For I is equal to 1, S takes the values minus and plus, so I'm adding P plus and P minus, dividing it by 2. Okay. So we just said the following thing. So mu I plus 1 is 2 to the I plus 1, and the S is going over minus and plus 2 to the I, P to the S. You can write it in the following way. I can say this is 2 to the I, S going from plus and minus to the I. Okay. I'm missing a 2 here. Okay. And this is only over all sequences of length I. To complete I plus 1, I can append to the S either a plus or a minus. Okay. So now I have to put here PS plus and the PS minus. Okay. So in a length I plus 1 sequence is a length I sequence followed by either a plus or a minus sign. So I write them both here. Okay. But the summations of these two things is exactly P to the S, because we just saw that any P, you plus it, you minus it, you average it, you get the original thing back. So this is the plus of the PS and the minus of the PS. So we get PS back. This is equal to mu I. So this is what we just observed, that the mu's are not changing. Okay. All right. Good. Now, what about the nu's? Okay, so the nu i's are again the same. To the I, the same summation. I guess I should use the ps squared. So I'm taking the average of the squares of these p's. Okay. So now, what about these things? How do they behave? Okay. Okay. Do I need that? I guess I do. Can I erase something? Erase this one? You're okay? All right. Or maybe I should erase at least this column here. Okay. So now let me observe the following things. If I square two numbers and add them, and take their average, okay, because I'm going to write this new I plus 1 in the same trick as we had done here. If I take the average of two squares, I should be write this thing down as like this. Is this correct, actually? Maybe, am I missing a factor 2 or something? I'm missing something, right? How about this? Is this better? Now it's fine, right? Because if I expand the squares, the cross terms cancels, the things add, and so forth. Okay, all right, good. So now, let me apply this thing to the following thing. So if I take the square of ps plus and the square of ps minus divided by 2, okay, right? Here I'm going to have the average of the ps minus and ps plus, which is ps squared, okay? Right. And I'm going to have here something, okay? I'm going to have here something which is ps plus minus the ps minus divided by 2 squared. So the difference between the plus and the minus versions of ps divided by 2 and then squared. Okay. In particular, this number is bigger than ps squared because this is a square, so it's always positive. So this is bigger than or equal to ps squared. Okay. And in fact, it's strictly bigger because this number is never 0 unless ps is close to the extremes already. Okay. But at the moment, this is fine. Okay. Now let's take a look at with the same trick to the new I plus 1. New I plus 1 is the following. By the same trick here, this new I plus 1 is 2 to the I plus minus to the I half ps plus squared plus ps minus squared. So this is fine. So now we have seen here that this is equal to, we just computed this quantity here, okay? And we just said this was bigger than, so this is equal to the thing that we have here. This is ps squared plus the square of the half of the ps minus the squared, okay? Good. So there are two things to observe here. One of it is that this quantity is bigger than ps squared, okay? And the summation over the s over all I length sequences divided 2 to the I is exactly a new I. So these news that we have these mu1 to be whatever, mu2 to be something, they are increasing. Okay, so these news are certainly, this is bigger than nu0, this is bigger than that, mu3 is bigger. So each of these new i's are bigger than the previous one. So this object here, this is larger than or equal to nu I. Okay? So the nu I plus 1 is at least as big as the nu I. So Dan seems unconvinced somehow. No? Okay.
But you have from the very first mu.
Yes.
Should that be 2 to the I plus 1?
This one here, this you're happy with. This is the lower one, okay. So this is 2 to the I plus 1. So we have that one.
The one below that, shouldn't that also be 2 to the I plus 1?
This is still new I at this moment.
Right.
This is the new I. We're okay. Oh, the next one, yes, this should be 2 to the I plus 1, but it's here.
Yeah.
So that 2 is the 2 to the I plus 1. So just as we did the mu I plus 1, there was the 2 to the I plus 1. I took the 2 to the I here, put one of the 2's inside, and I wrote the summation over all sequences of length I plus 1 as being all sequences of length I, and then the last 2 can be either plus or a minus. So there are 2 terms here. So this summation is coming from splitting out the s's which end in a plus and the s's which end in a minus. So the shorter s is the s in here now, which goes only over length I sequences. This half is coming from the splitting the 2 to the I plus 1 and 2 to the I and 2. Okay. Same trick here. Okay. So except that all the p's that we have are squared. So there's no exactly the same discussion here. So one thing is that we see that the new i's are a increasing sequence. At the same time, I had the following thing. You see, these numbers which are occurring here in these columns, they're all between 0 and 1. Okay? So these p's that I have are all between 0 and 1. Okay? In particular, squares are also between 0 and 1. So their averages are also between 0 and 1. Okay? So these news are bounded, because all of these news are at most 1. Okay? Now I have an increasing sequence of these news. So observe also, I now no longer, well, maybe I'll need this thing for a second. This one I erase. Okay. So we have all these new i's are certainly between 0 and 1, and I have an increasing sequence of these new i's. What do I know about this? All this increasing sequence bounded from above. What will such a sequence do? Can it diverge? Can it? No. So the convergent sequence. Consequently, the new i's converge. Okay. It's a convergent sequence. Okay. All right. So in particular, what's happening is the following. Consequently, a bigger board. Okay. Erase this. Consequently, if I take a look at the difference between successive new i's, this goes to 0. Okay, so the new I and new I plus 1 must get close to each other. Okay. Good. Okay. Now let me do something which is slightly better than just this inequality here. Okay. Let me say one more thing. Let's take a look at the difference between new I and new I plus 1. Well, I obtained that the new I plus 1 is bigger than new I by ignoring this term. If I hadn't, it would be exact. So the difference exactly 1 over 2 to the I, summation over all these I length sine sequences of the square of the PS plus minus the PS minus squared. The difference between the PS minus and PS plus, I divide by 2, I square it, okay, and then I sum over all s's. All right. Now, what do I know about this? I know the following. If PS is mediocre, okay, this number is at least something. Okay, so if I, for example, restrict this sum, this is at least as big as 2 to the I, all s's of this type, but I restrict it further to say that the PS is between delta and 1 minus delta. I'm only going to make the summation not over all the possible s's, but only for those s's for which the PS is not close to either to 0 or to 1. Okay? And the same quantity here. Okay? Since I'm ignoring some positive terms going from here to here, this is a lower bound because everything in the summation is strictly positive. Okay? No, non-negative. Okay? Good. And we know that for the PSs which are like this, we knew that this number is at least delta times 1 minus delta. Just before I erased, we had said that if P is between delta and 1 minus delta, the difference between P minus and P plus divided by 2 is at least delta times 1 minus delta. So I get here a number which is delta times 1 minus delta squared. Okay? All right. So now, this is now equal to this lower bound. Let me take this delta 1 minus delta squared out. Squared. And now a summation as to, I'm counting how many of these PSs are mediocre. Okay? This is now the fraction 1 over 2 to the I. Okay? And I have the number of S in plus minus to the I such that PS is between delta times 1 minus delta. Okay? So this quantity here is nothing but the fraction of unpolarized channels. Unpolarized in the sense of being delta away from 0 or 1. Okay? So they're neither close to 0 nor close to 1. They're strictly delta away. That's the fraction of these channels. Okay? Now what we just see, we saw that the difference between the nu I plus 1 and nu I is going to 0. At the same time, we know that this same quantity which goes to 0 is lower bounded by this quantity here. Now this is a constant. If I fix the delta, that's not changing with I. Okay? So consequently, what I have is that this fraction here, let me call this, let me give it a name. Let me say this is, sorry? Gamma, why not? Okay, so let's call it gamma sub I of delta. Gamma sub I of delta are the following things, just to give it a name. Gamma I of delta is the fraction of channels after I polarization steps that are delta or more away from being extremal. Okay. So these are channels whose erasure probability is neither less than delta nor more than 1 minus delta. Okay. I simply count a fraction of these channels after I iteration steps. That's exactly gamma of delta, gamma I of delta. So he knows the following. We now know the following things. So we have shown, we now know gamma I of delta is less than nu I plus 1 minus nu I divided by the square of delta times 1 minus delta. Okay. So this number goes to 0 as I gets large. Consequently, so this guy is going to 0. This guy is being a fraction. I'm just counting how many fractional channels. It's a positive number. So it is squeezed between 0 and something which goes to 0. Consequently, it must go to 0. Okay, so we have a theorem. Limit as I goes to infinity, nu I of delta, gamma I of delta equals 0. Okay, no matter what your notion of extremo is, so no matter which delta you pick, suppose you pick delta to be 0.0001, okay? If you make I long enough, if I make enough polarization steps, I'll be sure that the fraction of channels which are not polarized yet is going to be very small, as small as I want, as I make the polarization steps to go to infinity. Okay? All right. Yes, sir.
You derive this for the erasure channel.
We are only for erasure channel. We will do the same thing.
So is it that the channel must be symmetric?
So no. Very strangely enough, the symmetrical channel does not show up in the general proof. So for the erasure channel, I did this because I can get exact values of the difference between the P plus and P minus. Okay. For general channels, we're going to use the mutual information as instead of this P. Okay. So I'm going to do the same computation, but with the average of the mutual informations for the mu, which is again going to not change, and then the average of the squares of the mutual informations, okay, which will again going to increase. Okay. And then we have to bound the difference between the mutual information of W minus and W plus in terms of the mutual W itself to show that the this will be replaced by this sense is going to be replaced by the mutual information being between delta and 1 minus delta. Okay. And then we're going to derive a similar bound to say that if IW is between delta and 1 minus delta, then the difference between the mutual information of W plus and the W minus is at least some function of delta. In this case, the function was simple. It was delta times 1 minus delta. In the general case, it will be something more ugly but irrelevant. But I want to go through the argument once in a erasure case in which we can compute everything exactly so that you're on sure footing, that you don't fall off the stage, okay, and so forth. Sir?
We used x1 and x1 plus 2 to polarize the channel. If we can arrive at more combinations like x1 plus x2, x2 plus x3, x1 plus x3, some other combination, should we converge in lesser polarization steps?
So what you're suggesting is the following. Instead of combining channels 2 by 2, why do I start from just 2 channels W? Let me start with 3 channels. Okay, inputs are x1, x2, x3, and I make some more complicated transform between the U1, U2, U3 into x1, x2, x3. For example, x3 is U3, x2 is U1 plus U2, etc. X1 is U1 plus U2 plus U3. Would this also lead to polarization? And if so, would this lead to faster polarization? Okay. Now, the answer is that unless your transform is particularly stupid, okay, that if you find the right kind of transforms, they will all polarize. Okay. Whether they polarize faster or not depends on, again, exactly how you choose these, the transformation itself. This kind of work has been done by Rudy Urbanke, Satish Korada, and I think Eren Shashul. They were trying to come up with, well, first we had to figure out, okay, we haven't done the following things. Okay. We haven't seen how fast is it taking place now. Okay. And then we had to have a basis of comparison to see, okay, how fast it is there. Then we also had to compare, because we are combining, what you see is the following. At this moment, for each iteration, I double my block length. Okay. In yours, if you combine 3 channels, in each iteration, you'll be tripling your block length. So to be making a fair comparison, you have to make sure that you're not comparing apples and oranges. So the iterations in your thing are more costly in terms of block length than here. So we have to see the comparison correctly and then to see if they polarize better or not. Okay. In some cases, they do. So in general, this more complicated transformations will lead to faster polarizations at the expense of course, more complicated decoding too. So whether at the end you come out ahead or not depends on making a whole bunch of trade-offs. Is that, did I confuse you completely or?
So in some sense, this is depending on the initial erasure probability. So the value is a value of phi upper bounded by some relation depending on the relation between I and P.
So we're asking, will the polarization take place faster or not depending on the original P? Because I start with P already. Now, the following is true. If your P is already 0 or 1, you're done in 0 steps. Okay, so clearly how many that you have to do to get a certain delta depends on the P itself. Okay, so, but this is a uniform bound saying that the, actually no. Actually, this argument doesn't tell you how fast anything is happening because of the following. We only used a very mild condition that the news are increasing, the second moments. Consequently, difference between two news are going to 0. We have no idea at this moment how fast. Okay, in this roughness of the analysis, we don't really know how fast are these difference between the successive news are converging to 0. We don't know. Okay. So at this moment, we don't know how to answer your question. Okay. We will have maybe a better answer later on. Okay. Yes. Was there a question in the back? No. Okay. All right. Okay. Good. So now we have this. So by the way, I mean, this only shows at this moment that the fraction of mediocre channels are close to 0. Okay. Maybe I should also define the fractions of the good channels and bad channels. Okay. So maybe I should use gamma for good because it's G, but okay, anyway. So at this moment, gamma has been taken for mediocre. What do I do with my eraser? Okay, okay, here. So we also have maybe the following things. Let's define using this thing. This is the fraction of channels at level I. Channels after I polarization steps. That have erasure probability less than delta. Okay, these are the good channels, and beta I of delta. The same thing with erasure probability more than 1 minus delta. These are the bad channels. Okay, and these are the ugly channels. Okay, so we have the good, the bad, and the ugly. Okay, that's okay. So the ugly channels are disappearing fraction-wise. Their total fraction of the population is going to 0 by this thing. Okay, and these ones, these numbers had to add to 1, by the way, right? This is this. We had to have the fact that this plus this is 1 because the channels are either good or bad or they're ugly. There's nothing in between because all cases of erasure is covered. Small erasure probability you are here. Big erasure probability you are there. Neither you are here. So all cases are covered. So we know that the 1 is equal to alpha plus beta plus gamma. Okay. We also have the following things. Now, each of these channels here have erasure probability at most delta. Okay. So if I look at the sum of the erasure probabilities of all the channels, okay, whose average we know to be P, okay. So P is the mu. Okay, so this mu I P is equal to mu I know that. Okay, for each I we have this. Now, what are these guys contributing to this mu I? They contribute at least 0 and at most delta, right? So I can have, for example, here, I have delta times alpha I, okay? These are contributing at most 1 to the erasure probability average plus beta I, okay? And these guys are contributing at most 1 minus delta to the erasure probabilities sum. Okay. Let me upper bound this thing by gamma I also. Okay. At the same time, the same object here, these alpha guys are contributing at least 0 to this thing because everything in the alpha guys have erasure probability between 0 and delta. So this is 0 times alpha I. Okay. These guys are contributing at least 1 minus delta. Sorry, at least delta to the beta I. And so are these. Okay. These guys are also contributing at least delta to this p here. Okay. All right. And the limit, I know the following things. In the limit as I gets large, this is not there. Gamma I goes to 0. Okay. So alpha and beta, they sum to 1. Okay. This guy, these guys aren't there either. Okay. For large I. Okay. All right. So what I have is that the beta I, and if delta is small, okay, if delta is small, this is saying that the beta I is at least p. Am I doing this thing right? Then I want to have here something else. Yes. You're absolutely right. I can put here that. Okay. Okay. I further upbound it by 1. But that's let me write it like this. I think it is better to do so. Okay. All right. So now, what do I have here? What I want to conclude from here, let me just tell you what I've tried to do, is to say that the beta I must be getting close to p, and the alpha I must be getting close to 1 minus p. Because I'm going to argue that otherwise there is no way to satisfy both this and the fact that the average of these things is equal to p. I'm never going to get. Okay. So now why I'm not seeing this thing is a question here. So I'm getting from here only that this beta I is at least p. Yes. Yes. Put that in the first, and I'll get the alpha is less than 1 minus p. I want to get something that alpha is also close to 1 minus p too, because I want to get very many good channels. For this, I will do something more tricky, it seems. Right? This is it looks like I have to take a look at this thing here. Okay. Okay. These alphas and betas. Right. For the betas, the minimum error is 1 minus delta. Thank you very much. This will have us. Okay. Hi. Thank you. Okay. I was wondering what I was doing wrong. Okay. Because all these channels in the beta, they have erasure with at least 1 minus delta, so they contribute here this. Okay. So if delta is small, okay, what you see is ignore this term. This is fine. For delta is small, which means that the beta is upper bounded by p over 1 minus delta. If delta is small, that is p. Okay. And then from here you'll find that the beta is also lower bounded by p. Okay. So from these things, beta is between essentially p. Okay. This is for I large and delta small. Okay. Large I, small delta. This is coming from here, and from there, okay, you also get the same inequality from the top. If delta is small, this is essentially 1. I is large, these are essentially 0. So we get a upper bound on delta as being that. Okay. Consequently, alpha is also close to 1 minus p. Okay. So if beta is close to p, alpha is close to 1 minus p because they sum to 1. Okay. All right. Good. Same appears here. Okay. All right. Because we see that these limits that the gamma goes to 0 is true regardless of delta. So you can make delta as small as you want to get these inequalities as close as you want to 2. Okay? Good. So now this one says that the polarization happens for erasure channels. If you do these steps many, many times, you'll end up with a tiny fraction, a vanishing fraction of ugly channels, and the fraction of good channels is going to converge to 1 minus p. Fraction of bad channels are going to converge to p. Okay? All right. Maybe to be clear, I should also tell you what would be, in fact, the coding scheme at all. Okay? We have started from a number of copies of this W. Maybe let me draw this thing for 8. Okay. So we start by combining these things to create the, from 8 copies of W, I create 4 copies of W minus and 4 copies of W plus. And I combine the W minuses 2 by 2. To create 2 copies of W minus minus and 2 copies of W minus plus. And then I do the same thing with the W plus channels. Okay. I now have here 2 copies each of W minus minus, W minus plus, plus minus, and plus plus. And then now I combine these 2 things together. So here are 2 copies of the W plus plus. So this creates the 1 copy each of W minus 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 all the way to W plus plus plus. Okay. So now, what we know is the following thing. So if this W was, suppose this was 8 is infinity, okay, or 8 is very large, okay. So we know that the inputs through these things are all seeing almost extremal channels, okay. Some of them are seeing good channels, some of them are seeing bad channels. Suppose, for the purposes of discussion, that 3 are seeing good channels and 5 are seeing bad channels, and the 3 which are good are, let's say, this channel is good, this channel is good, and let's say this channel is good. Okay, these are the good channels, the ones who form the alpha fraction, 3 over 8. Okay, and then the bad and the mediocre channels together, they form the other 5 of these channels. Okay, so maybe 4 of these things are bad, and 1 of them is mediocre. Okay, suppose. Okay. So now, my coding scheme will then be the following stuff. I will freeze the inputs to the non-good channels, either bad or mediocre channels, to known symbols. Okay. I could do them by doing coin flips, or in this case, because of the symmetry, somebody raised this issue about channel symmetry. If you have symmetric channels, it doesn't matter which ones you set them to. Okay. If you have asymmetric channels, you have to be careful as to what you're setting these symbols to is going to be important. Okay. So we freeze them to 0. Okay. Are you all electrical engineers? Yes? Okay. In that case, I'll just put a ground symbol here. Okay. Yes, Dan?
How do we know which inputs correspond to bad channels and which correspond to good channels?
So each of these things, they correspond to a particular W with a particular sign sequence. Right? So for the erasure case, I could simply compute the erasure probability of each, which, as we did here. So I knew where these 0 point blah blah numbers were coming from. Comes from the... But you're absolutely right in the following sense. I mean, you give me the channel, I'll do this transform. I have to figure out, I mean, I know that at the end of this thing, by this theorem, that the so many fraction are going to be good, such fraction are going to be bad. But apart from the 2 extremes, this certainly is going to be good, because it's the plus, plus, plus. Okay? And this is bad, it's the minus, minus, minus. Okay? But the other ones, okay, I don't know among this 3, among the 6 2 more are supposed to be good, but which ones? Okay. This requires a computation, so I'd really have to, yes, we had to do this thing. The thing on the computer for the erasure channel is fine, because we computed, in this case, this is done offline. Yes. That's the code design problem, right? So this is not the coding problem. It's not the encoding problem. It is the design of the code problem. For the erasure case, this was easy, because we knew exactly what is the erasure probability of the synthetic channels are. We could compute explicitly. If you have a more general channel, that's a pain, because you see each of these channels are binary input. But take a look at the output alphabet sizes. Suppose you started from suppose we started from a channel with, such as the BEC, a ternary input. The W plus or W minus is going to have in principle 9 outputs, because its alphabet is Y1, Y2. Each of these Ys are ternary, so the output is 9-ary. For the BEC, it was easy because we could collapse this 9-ary stuff into, again, 3 symbols, because we said that these things are equivalent to being erasures and so forth. That was easy. But in general, okay, they may be all different, to be kept track differently. W plus is even worse, because not only has these 9 possible Y1, Y2s, it also has 2 possible U1s, 0 and 1. So you have an 18-ary channel. Now, if you go to the plus channel of the plus one, the W plus plus, you have 18 squared, which is 3 and then 20 something, times 2. So you have 600 outputs. The next plus operation is going to square the 600 and then multiply it again by 2. So end up with channels whose output alphabets are humongous. And to try to keep track of is this channel good or bad, and then to compute the next iteration is going to take a huge amount of computational effort, unless you're clever about this. Okay. And there's a way to be clever. So I'm hiding all this computation which needs to be done in the non-binary erasure case into saying, okay, this can be done perhaps, but haven't shown you how. Okay. But it's possible to keep the computation effort for the construction also to be also reasonable. Okay. At the end, well, okay, so it's going to be almost linear in the block length, strangely enough. If logarithm, you don't count, okay? If the log n doesn't count, it is linear and the block length is sufficient. Okay. So I'm going to freeze the inputs to the non-good channels to 0, okay? And I'm going to put here my data symbols, okay? In this case, whatever it is, U5, U7, U6 or something, okay? And then from these ones, together with the zeros, I'm going to have a mapping between these 3 bits of actual inputs to the 8 coded bits that you feed to the W channels, okay? So use the channel W 8 times with the coded bits. At the output, you're going to receive Y1, Y2, Y3, Y8, and then we'll figure out how to decode this Ys into these U's that we have there, okay? So receiver, when he needs to decode the U1, he doesn't decode it, he knows it to be 0. So the U1 is challenged a bad channel. So if you had estimated based on the Ys alone, you'll be in terrible shape, because the erasure probability, you'll always get erasures, okay, from the W minus, minus, minus. But fortunately, you know that the U1 is 0 already, so no effort is needed. The decoder simply decides U1 immediately. Okay? So this is done at the code design time. Similarly, U2 is probably here, U3 is there, and so forth. You do these. Okay.
So remember, is there any sense of trying to do it in such a way that you're decoding the frozen bits first, because that gets you off to a good start, because you know them, or is that?
In the way that we constructed this, it seems like you have to decode them at the right order, and then you take the frozen bits as you need them, as they come. Okay. I'll try to show you the decoding structure also. At the moment, I want to note the following things. So first of all, if you saw how I draw this diagram, it was done in 3 stages. The first stage, which was to form from W's the channels with only a single sign, either the plus or the minus sign on them. And then we had a second stage here, from which we constructed channels with 2 signs on top, the minus, minus, and etc. And the third stage was this. And of course it is 3 because it is 8. 2 to the 3 is 8, so we go in log n stages for a block length n code. N is always a power of 2, so block length is always a power of 2. you do log n stages. And you see, in each of these stages, we have exactly half of these lines has a plus sign. Other signs are simply going through. Okay? So number of XORs in this whole diagram is operations is exactly, if n is the block length, this is the 2 to the power number of stages. Log n divided by 2, because in each stage you have half n XOR things and you have log n stages. Okay? So this is to say that the encoding operation is actually is very easy. So to encode your data bits to get to the coded bits, it only takes n log n iterations to do this. N log n binary operations. It's not even real multiplications. It's simply multiplications or additions and multiplications in the binary field, particularly easy here. So the encoding effort is rather low. It's like an FFT. In fact, the diagram probably, if you're signal processing background, this looks like just like how you compute the FFT of a sequence. It's a butterfly structure. Okay, so this is implemented like that. Okay. We shall see later on that the decoding effort is also similar, is the same. In n log n, this time real additions and multiplications, you can do the decoding too. Okay? So decoding effort is also going to be n log n. That is particularly surprising, that the encoding effort is being low is maybe not that amazing. Okay? However, the decoding effort only being n log n is a surprising phenomenon, because if you think of what would be the complexity of maximum likelihood, it's of course exponential in the end. So, and this is not even n squared. Okay, so, but in some sense, I mean, of course, you cannot do less than n, because you have to, any machine which takes a look at the output of the channel has to read n channel outputs. So you can never beat order n. It's also print the n of these U's has to be printed out. So any computer which is going to decode a block length n code has to make at least n operations. So a modest increase of multiplier log n, you can decode things and then achieve capacity and so forth, is surprising. Okay, good. I guess this is a bad time to try to start talking decoding, because we're just at the 2 minutes before the break. Or am I half an hour off? No. How long have going for an hour already? 12 is the break. Okay, but 2 minutes warning. So Kanan has a. In 2 minutes? No, but do you have to leave right now? Okay, then I'll do it for you. Okay, so I'll do it for you, but maybe we'll do it at the lunchtime. I'll do it for you because you're off. Okay. All right. So okay, questions at this moment. A very interesting question. I mean, but this is maybe something which we should pose to Erdal, who invented these codes. I can make a guess. Okay, for this. So Erdal had been working on a topic called sequential decoding for many years. Okay, so I think it's essentially a close to 3-decade effort at this moment. But at the time the codes were invented, it was a 2-decade effort at that time. So sequential decoders are meant for convolutional codes, okay, and they're known to work well at rates not up to capacity, but a number called the cutoff rate. Okay, I think Dan had a number of plots in which he showed a cutoff rate for a Gaussian channel, and said that for many, many years.
Kind of ignored talking about yesterday.
Right.
Dotted lines.
Dotted lines in these slides yesterday. So it was for a long time believed to be what was practically achievable. Capacity was something that nobody thought that you would ever be able to achieve, but cutoff rate was perhaps possible within computational effort, despite some evidence to the contrary. There were codes which were beating the cutoff rate, but whether they were practical or not was a eye in the beholder kind of questions. Now, however, unlike mutual information, which is preserved under processing, cutoff rate is not. You might be able to improve cutoff rate by doing processing. So Erdal's idea was to do these operations, such as this polar transform, to improve the sum cutoff rate. So you start with two channels whose cutoff rates are, let's say, R0, and you create new channels whose cutoff rates are R0 plus and R0 minus, but with the property that the sum of these two new R0s, R0 plus plus R0 minus, is more than twice the R0 that you started from. You keep doing this and hope that perhaps you will achieve that the average cutoff rate of the synthetic channels are going to be close to the capacity of the underlying channels, and then use sequential decoding with convolutional codes to transmit data reliably across this. Very surprisingly, I think to him too, that these transforms are in fact in such a way that the synthetic channels are so good or so bad that it was pointless to do any further coding on them. So this using convolutional codes and the sequencing was not necessary. You could simply send uncoded data on the good ones and send constant symbols on the non-good ones, the ugly ones and the bad ones, and still do arbitrarily close to capacity as you wish. So that's, I think, how polar codes were come up with. In a sense, I guess they came from a neither encoding nor decoding points of view, because the points of view that were taken ended up not being used at all. So if any point of view was there, it was for convolutional codes and sequential decoders. But at the end, those disappeared, so you only end up left with the channels themselves.
So that's maybe it from the point of view of the channel.
Yes.
In some sense, it's interesting that you get this balance of complexity between the encoder and the decoder, which almost says that it's the right kind of design.
Possibly, yes. But it's also the construction that we have here. There's no coding theory in this. I mean, if you teach coding theory, you start with very different concepts. So we talk about minimum distance. You talk about algebraic structures. You talk about graphs and so forth. Here, there is none of this. It's a purely at this one you don't see it yet because we did the example only for the BEC. So it sort of hides any information theory. You can teach this thing without knowing any information theory. I suppose you had never heard of entropy. You never heard of mutual information. This thing still can be taught to a high school class if you want for the BEC. When we go to the more general case, I'll have to talk about entropy and mutual information and so forth. But you're right that the pure information theory will get you to construct polar codes without any notions of coding. So this could have been done in the 1950s. Already, but wouldn't have been practical though at all. I mean, even if people invented this, they would have thrown it away, I think, just like the LDPC codes were. Because we haven't said anything about how large the block length needs to be, how big the I should be, and so forth. We have not touched these things at all, and there are still issues there. It's not that the
bottle was about
yeah, also the bottoms of these bottles are somehow not quite flat, so there's always a bigger wobble than what one imagines. Well, further questions? Sir?
Can we apply this idea on AWGN?
So AWGN with binary inputs, you certainly can. So the construction here never talks about the output alphabet size at all. So the output can be anything that you want to. Could be reals, no problem there. The input needs to be binary. So as long as you reduce your channel to a binary input channel, you're fine. And if you're unhappy with this, I'll tell you a few things about how can you go to higher alphabets. The same thing can be done if you replace this plus operation by any reasonable group operation. Things will polarize also. Okay. There are certain tricks there, so I can get to this later on. Or if you wish for the AWGN, you could try to do a multi-layer design. You could represent the input to the AWGN as bit plus half of another bit, quarter of another bit, etc., and then do polar code designs for each of these bit streams, combine them and send across the channel. That'll also work. So there's a way to adapt polar codes to AWGN too. And they do quite well, actually. Are there better codes? I mean, certainly. Now, I guess that's a question to be answered in the following way. So, apart from this spatially coupled codes, polar codes are the only codes with the following properties. They are capacity achieving. So, unlike LDPCs are close to capacity, but they're not capacity achieving. So, you can always choose a rate for which the LDPC code cannot do, and the polar codes can. So consequently, for that rate, polar codes will beat the LDPC codes eventually. Okay. They also have explicit encoding and decoding structures. And secondly, they're constructed explicitly too. So when you take an LDPC code, I have nothing against LDPC codes, by the way. They're very nice codes, and they're very practical codes, eminently so. They're used. Polar codes are not, right, at the moment. So, but there's always a random component in them. So you have to there's ensemble of LDPC codes. You show that the ensemble is good. Consequently, if you pick a random element of this ensemble, you're highly likely to have a good code. Okay. But you should test it. I mean, if you just pick up a random LDPC code, without testing it, you should not use it because you might be unlucky. And if you wish to make a guarantee that this LDPC code has error probability less than 10 to the minus some big number, then this test can take a very long time. So for practical error probability, say in wireless, if you want 10 to the minus 5 and so on, no problem. You can test, send 10 million bits, okay, and then you will know what is the error, if you have picked a good code or not. But if you want an error for 10 to the minus 15, the amount of testing you should do is much bigger. Polar codes, by contrast, there's no random component in them. So you know exactly what you're supposed to do, which things to pick, and you also have explicit error probability guarantees. You know that the code that you constructed, if you believe that your channel is the channel that you think it is, right, then it has error probability at most blah blah. Okay, so those three properties are unique to LDPC codes. I guess even the spatially coupled ones, they will have a random component in them. So they are like Reed-Solomon codes in that sense. So they are very explicit codes. So that might have some attractive qualities in certain applications. So
I can add to that too. I think when you put in structure to LDPC codes, then they no longer have those ensemble-like properties. Here, right, in a sense, you're getting the structure,
right,
along with the capacity function property.
That's right. So it's a bit of a surprise. I mean, the capacity achieving is I think had these been invented 10 years before they were invented, would have been a bigger deal, I think, the polar codes. They still might become. These are block codes. LDPCs are all block codes because the transform here is good. I don't know of any. I mean, can we build convolutional codes based on polar codes? Perhaps by these. It's a good question. So, yes. Could you do this? Yes. Could you do? Yeah. Could you do what Dan suggested to break up the parity check matrix, which corresponds to polar codes, because they'll have one, and then to stack them in this the diagonal triangular ways to construct convolutional codes out of them? It might well be possible. I don't think that it's been done.
I don't know whether there would be an advantage.
I don't know whether either. Yes, it's unclear.
What are the block length comparisons at which the same kind of performance happens between LDPC and polar codes?
Polar codes are a lot longer, not longer. I don't know, honestly. However, people do the following things. We suggested this successive cancellation or successive decoding. I'm not sure what are we cancelling. You decode U1, U2, etc., so forth. That's the decoding strategy. On top of this, you could put a list decoder. You can say that let the polar decoder not just make one decision. If it is not completely sure about deciding a particular U, let him actually keep both and continue on both lines, and then split this thing. Let's say up to 5 splits you allow, so you have 32 copies of your decoder if you wish. Okay. And then you put a mild CRC on your overall code so that you can decide which of these 32 candidates that you have is the one that you want to choose. If you do that, you actually do get very good performance at much shorter block lengths too. So it seems that Huawei is interested in pushing these things for wireless standards. I'm not sure if they're successful or not, and they're pushing it for, I think, a control channel, which you need reliability guarantees more stringent than perhaps the data bits. So, and there I think that the lengths are reasonable, but you modify the decoding method and so forth. It's not the same. It's not pure polar codes anymore, but I mean, it's not such a huge thing either. You can also afford to have much bigger block lengths for the same complexity, because the complexity decoding of polacode is small with the SE decoder. So whereas the LDPC for that block length would be impossible. So some of these things I'm shaky on, by the way. I'm not an avid follower of all the literature on any of these subjects. So I'm not a coding theorist. So I'm not even sure why I'm here giving lectures on codes. It's not coding theory, but the questions that you ask are coding theory questions. So the questions you ask are coding theory questions. So I'm not a complete expert on those. But I'll make up whatever I don't know, and then you can. It's part of being a professor. I'm a professor who comes with the job that I can pretend to be very confident about something and then convince you. All right. Okay.